Okay, so for today, we're going to wrap up everything to do with only one component. So we've got a couple of properties that we have to go over for phase changes, just a little bit of house cleaning stuff. And then on Friday, we're going to hit it with multi-component systems. So on Friday, we're going to go through how do we reformulate all of thermodynamics to account for the fact that there are multiple components in a single system. So we have to rederive some new terminology, but then we'll have a way to sort of organize and characterize multi-component mixtures. Then we'll move on, obviously, to multi-component, multi-phase systems. And once we get to the point where we're defining multi-component and multi-phase, that means we've basically fully formulated thermodynamics. And at that point, it's just approximations. How do we approximate it for a liquid-liquid system, for a vapor-liquid system, for liquid-liquid vapor systems, and so on and so forth. So after we've really formulated everything, then it's a matter of splitting it down into different applications. And the reason for all of this, and the reason why I like this procedure, is because there's so many different ways to model things. There's so many different equations of state. And each field seems to have a different way of modeling it. So since everyone here is going to go into a different field potentially, I think it's best just to say, okay, I'm not going to focus on one particular industry, that whatever industry you go into, you can just grab something off the shelf and you know the fundamentals of how to apply it. So that's the general framework of why I like to walk it through this way. But for today, we are going to go with cleaning up on some stuff here. And the pencil is dead.
So I hope I don't have to write with my finger.
And I'll have a really high quality presentation. Okay. So first we're going to go over the Gibbs phase rule for multi-phase. So for any single component, we know, and this is based on basically the Gibbs phase rule saying that U, V, and S, those are our main sort of variables of the universe according to classical continuum thermodynamics is what we're going over. So that means if I want to know U, I just need to have some function of V and S. And this will fully define our system. So for example, if we have some temperature and pressure, let's say this is 20 degrees C and 1 atmosphere. This is for water. We are in the phase of liquid. There's no other state that water can exist in because we fully define the system, and water's properties dictate that at these conditions, that's how it has to be. If we go to 150 C at 1 atmosphere, it is a vapor. It is not a gas because it's not supercritical. So the vapor is a subcritical fluid in the gas phase, but typically we call gases things that are supercritical. Like nitrogen and oxygen, they're gases at room temperature and pressure because their critical point is much, much lower conditions than where we're at. So we're at that supercritical positions. But water vapor at 150 degrees C, that's not above its critical point, so we refer to that as a vapor. And then, in case you guys were curious, obviously at minus 20 degrees C, water is a solid. We're just trying to drive home the point that for all of these, they have 2 degrees of freedom. As soon as we use up those 2 degrees of freedom, we have fully fixed and assigned the system. That's for a single component, single phase process. Now I really think that the Gibbs phase rule is undersold in terms of its importance to the development of thermodynamics. Because when we're expanding all of these functions, right, the dH, the ds, the du, we have to choose 2 variables to expand into. But you don't really ever talk about why it's just 2 variables. Why isn't it 3? Why isn't it 4? So the Gibbs phase rule I really think is a critical component of thermodynamics, and its importance is sort of up there along with the first and second laws is what I think, in my opinion. Okay, so if we are to define the Gibbs phase rule for a multi-phase system, the degrees of freedom, we have 2 for each phase. Right, so for phase 1, we define 2. For phase 2, we define 2. But we're going to have some dependencies. There's going to be some dependent equations that are going to limit the number of degrees of freedom. So because everything that we're doing in thermodynamics is equilibrium thermodynamics, right? We cannot predict how things change as a transient all that well using this sort of fluid phase equilibrium, right? So we can only tackle systems at equilibrium. So if we have multiple phases at infinite time, they have to be in equilibrium. And so we have a couple of rules of how that works. So we have thermal equilibrium. In this case, the temperature of phase 1 is equal to the temperature of phase 2, and so on and so forth for all of the potential phases that we have in the system. So this results in P minus 1 equations. Right, because if we have 2 phases, right, we have 1 equation. If we have 3 phases, we have 2 equations. So whatever number of phases we have, the thermal equilibrium dictates that the temperatures have to be fixed across those phases, and then mathematically that results in P minus 1 dependent equations. Same thing with mechanical equilibrium. We get P minus 1 equations. And chemical equilibrium. And this is where the Gibbs free energies are constant, P minus 1 equations. So if we substitute everything together, the total degrees of freedom is 2 times P. For every phase, we have 2 variables that we need to fix, which is basically the fundamentals of the Gibbs phase rule, minus 3 sets of P minus 1 equations. So if we do the math, the degrees of freedom from the Gibbs phase rule gives us 3 minus P. So if we were to put this into an application, if we say we have vapor-liquid equilibrium, how many phases do we have in vapor-liquid equilibrium? 2. So that means we have 1 degree of freedom, which means that we can either choose the temperature or the pressure. So in vapor-liquid equilibrium, oftentimes we'll run into a T, X, Y diagram where we're changing the composition and we're changing the temperature and figuring out where the phase change occurs. What is the boiling temperature? What is the condensing temperature? Or rather, the bubble point and the dew point. Or we can write this as the PXY diagram. We fix the temperature and we vary the pressure. In addition, the vapor pressure is a function of only the temperature. So if I know the pressure of the system and its multi-phase, I know its exact conditions. If I know the temperature of a multi-phase system, I know its exact conditions. If I have the triple point, I have 0 degrees of freedom because I have 3 phases in existence at the same time. So I have no power to control the triple point whatsoever. When we have the coexistence of solid, vapor, and liquid, everything is locked in. So I forgot, I just reminded myself now that I usually like to show a video when we talk about the triple point, critical point, and things like that. I'll show those videos on Friday. They're kind of neat. Okay, so the Gibbs phase rule, it defines the minimum amount of information that we need in order to say what the state of the system is in terms of the phases. But it doesn't tell us everything we need to know about the properties because we don't know how much material is in each phase. So in addition to the Gibbs phase rule, we also need to have access to a material balance to some extent. What is the fraction of the material in each of the phases? And then from there, we can piece together what is the total enthalpy of the system and what is the total entropy of the system. Right? It's a 50-50 mixture. That means the liquid is bringing half of the enthalpy and the vapor is bringing half of the enthalpy. Does that make sense? So it doesn't tell us absolutely everything we need, but it defines the states for the phases of the matter. Okay. Any questions on the Gibbs phase rule? Okay, so let's talk a little bit more about phase transition properties. So we're going to start off with our chemical equilibrium criteria, that the Gibbs free energy of phase 1 has to be equal to the Gibbs free energy of phase 2. Likewise, any external changes to the pressure or temperature of the system, right, will change the Gibbs free energy. If the system is to stay in equilibrium, those changes have to be balanced out. So if we substitute in our combined first and second laws in place of the Gibbs free energy, we have V dP minus S, so V of phase 1, S of phase 1, dt, all of this for phase 1 here, is equal to the same thing for phase 2. These two phases are in equilibrium, so the temperatures and pressures are constant. So what we're going to do is we're going to just rearrange this expression and solve for dP dt at constant G, which we've already sort of satisfied because we said these two things are in equilibrium. Bingo. We're not quite at the Clausius-Clapeyron. We're just doing the Clapeyron equation right now. So this is S of phase 1 minus S of phase 2. And this is equal to delta S divided by delta V. So we're almost quite there. There's another way that we write this. We can write that the Gibbs free energy is defined as H minus Ts. So if we have two phases that are in equilibrium, their delta G is equal to 0. So we can write that across the phase change, delta S is equal to delta H. So we'll write out the Clausius. This is the Clapeyron equation. We can also write this then as delta H over T delta V. This is the Clapeyron equation. The Clapeyron equation is something that you guys probably won't ever use too much in any practical application, but it is how we actually measure a lot of these properties. So it's much easier to measure the vapor pressure of a two-phase system and how it changes as a function of temperature than it is actually due to the calorimetry experiments to measure the heat of vaporization. So but through using the Clapeyron equation, we've made no assumptions whatsoever So we can actually very trivially calculate delta H, delta V, delta S of phase transitions by just measuring the pressure, which is very convenient. So the Clapeyron equation is really useful because that's actually how they measured a lot of the physical property data. Now, if we approximate the Clapeyron equation, if we say that the vapor phase is an ideal gas phase, that means that the specific volume of the vapor is much, 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 much greater than the specific volume of the liquid. And that we can approximate it as RT over P. Therefore, the delta V of the phase change is just approximately going to be equal to the volume of the vapor, because that liquid volume contributes so insignificant amount. And there we can drive the Clausius-Clapeyron equation. Oftentimes you'll see this written in a form that looks like this. So this is something that they really like to do a lot in thermo, and it threw me off for quite a while. But it's just a calculus trick, actually. And so sometimes you might encounter this at some point in the future. So I'd like to kind of go over it real quick, how they actually come about it, if I can do it well. So if we say that this is dy dt is equal to d ln of p dt, right? So we can rewrite dy dt as equal to, let's see if I can get this right, dy dx dx dt. In this case, the p here is the x, and that this function here is the y. Just using, I think this is the chain rule, if I remember correctly. In this case here, right, if we take dy dx, since it's a natural log function, this is 1 over x times by dx dt. And then if you move this 1 over x, it's basically moving it over to this side of the equation. I guess I could have just left the x as a p. Does that make sense? So it's just a math, I think it's the product rule and the chain rule. I think it's the chain rule is what it is. But anyway, so that's how you can remove this PSAT term here. And you can kind of lump it in with the other side by taking this little natural log trick. But it's just a calculus trick. But they seem to do it all the time in thermodynamics. That's why I like to bring it up. Okay, one last comment about the Clausius-Clapeyron equation. Who's familiar with Antons Equation for vapor pressures? Hopefully everyone, because that's something that people in chemical engineering use in thermo, in design, in process engineering all the time. So the Anton equation form is usually natural log, or it could be log base 10. But it is the vapor pressure that has the form like this. It is an exponential function. Now this is an exponential function because the Clausius-Clapeyron equation is an exponential function. So if we approximate this Clausius-Clapeyron equation, and we say that the heat of vaporization is approximately constant, we can integrate it, and we get an expression that looks like this. It doesn't look exactly like Antons equation, but the form is pretty similar. So Antons equation is very convenient because it is not a polynomial fit. It actually has a fundamental theoretical basis that the vapor pressure should be an exponential function of temperature, which means that it's not the end of the world if you go a little bit outside of the correlation range that it lists in the book. For heat capacities, it's a big no-no. Do not go outside of the range because it is a dummy fit. It has no theory behind it. It's just a polynomial fit that seems to do the data well. And the reason why they chose a polynomial fit is because it is very easy to integrate, because integrating the heat capacity is basically its job. But in terms of the Clapeyron equation and how it relates to the Anton equation, write that here. Right, it has a functional basis. It's exponential. So your uncertainty of how accurate your vapor pressure fit is going to go down, but it's not going to explode catastrophically necessarily. Okay. Now another term that you guys may have heard of is a first order phase transition. Does that name ring a bell to anyone? It's quite common, especially in sort of physics literature, talking about phase transitions. So a first order phase transition is a vapor-liquid transition, a solid-liquid transition. But where it gets the term first order phase transition is based on discontinuities in the Gibbs free energy. So G is constant across phases. The volume and the entropy, they are not constant. They are very certainly not constant, especially the volume if we can think about it from physical reality. Right, the volume of liquid versus the volume of water vapor in equilibrium, those are definitely not the same. Entropy, definitely not the same. Right? The volume of the gas that it occupies gives it a tremendous amount of entropy. So a first order phase transition is because the first derivative of the Gibbs free energy is discontinuous. So dg dt at constant p, that is equal to minus S, discontinuous. dg dp at constant t is equal to V, discontinuous. So that is why we have it's called a first order phase transition, is because the Gibbs free energy is discontinuous. They also have a thing called a second order phase transition. And this is where the second derivative of the Gibbs free energy is discontinuous. Now this doesn't happen very much in chemical engineering processes, but it is more so relevant in material science and metallurgy. So in this case here, the second derivative of the Gibbs free energy is discontinuous. And so this is more likely to occur in solid phase transitions. So one example is a quartz crystal structure change. If you change the temperature and pressure, the minimum energy configuration of the crystal pattern may be altered. So its density really isn't changing that much. Its entropy really isn't changing all that much. But because the bonding is rearranged differently, it has a different heat capacity. Because the heat capacity of solids is very much related to the bonding geometry. Yes?
What do you mean exactly by discontinuous?
So, if we are looking at a plot of the, let's say, volume as, let's say, the phase. So over here, it's a liquid, and then it jumps up instantaneously and goes over here for the vapor. So that it's not moving from one phase to the next. There's a step change in the material property at that interface. But if you were to look at the Gibbs free energy, the Gibbs free energy of, let's say, going through a water bubble or something like that is constant. If they're in equilibrium, that interface doesn't change anything. But as a function of position in real space, as soon as you cross that interface, there's an instantaneous jump of the material property in the case of entropy and in the case of volume. But through math, you can also show that, of course, the enthalpy changes instantly as well. Okay. So, speaking of droplets, the last thing we're going to cover is small systems. Most everything that we will talk about are infinitely sized systems. Right? So the geometry of the phase doesn't matter. Right? You can think of it, if we're in liquid vapor equilibrium, we have an infinite ocean of liquid and an infinite sky of vapor. That is essentially what we are doing with all of our calculations. But that's not the real world. So in the real world, we have interfaces. So if we have a mixture of A and B, we talked about this a little bit earlier, but due to how molecules behave, under all circumstances, essentially, A molecules prefer to be with A, and B prefer to be with B, unless you've got some sort of ionic system and things like that where they dissociate pretty heavily. But in general, let's say we have a covalently bonded system. The way that the electrons slosh around inside of those molecules makes it line up just so perfectly with all the other friends. Changing that bonding structure a little bit alters the way that they sort of interact with one another. So when we have an interface, right, we have molecules of A on top of molecules of B. What's going on a molecular length scale is that you have some sort of interaction energy between A and A molecules and B molecules. Now, we've talked about this many times as sort of a Leonard-Jones potential. So if we are to look at, let's say, for example, A interactions, it might look something like this. That you have some equilibrium position right here. This is, for example, this could be U as a function of the separation distance. There's some sweet spot that has a minimum energy. But if you have a cross term, so this one here would be A interactions. If you have some cross term, it'll probably be something a bit more like this. So those A-B interactions are slightly higher energy, right? You don't quite minimize the energy the same amount when you have two different components in contact with one another. Now, this doesn't have to be A and B are different molecules. It could just be that A and B are different phases. Liquid water versus vapor water. That forms an interface as well. So what that means is that macroscopically, this interface right here, forming this interface takes effort and it takes energy. So all of thermo is basically trying to minimize the Gibbs free energy at constant temperature and pressure. Right? That's based on just the first and second laws put together. So the goal here is to minimize the Gibbs free energy. Part of that is the enthalpy. Part of the enthalpy is the internal energy, which is what we have right here. So we're trying to minimize the energy. So that is why interfaces are flat, unless we get to small systems. Because if we have an interface that looks something like this, we have increased the contact area between A and B. Now that creates energy. That energy has to come from somewhere. So obviously the system doesn't want to spontaneously just form an interface. And that's also why when you have droplets, they are spherical. Because a sphere maximizes volume with minimum area. So the spherical droplet shape is basically predicted based on this concept of a surface energy. The molecular origins of the surface energy have to go back to this binary interaction between the molecules. A wants to be with A, B wants to be with B. So this is called surface tension. Oops, if I can spell. I like to think of it as surface energy. Joules per square meter. Those are not the SI units of surface tension. We'll cover that in just a second. But anytime you hear surface tension, I like to think of surface energy. So when you're reducing surface tension by adding a surfactant or something else to your compound, what you're doing is you're softening the blow of having A and B in direct contact with one another. If you're adding in some sort of a surfactant, right, to this interface here, you might add in a surfactant where it has one group that's a little bit friendlier to A and a little group that's a little bit friendlier to B. This lowers the surface tension, but the way that I like to think about it is it lowers the surface energy. It lowers the penalty for those two phases to be in contact with one another. So the SI units of surface tension are Newton meters. And we typically write it as sigma. So this is Newton meters. Right, so we can relate this back to surface energy. So I'm going to say that this is the same thing as an energy over an area. So energy is joules per meter squared. A joule is a Newton meter divided by meters squared, and that gets us back to our SI units of surface tension. Yes?
So I'm assuming in dynes per centimeter?
That's the same thing. Dyne is a unit of force.
Okay.
That would be a, actually I don't know, what is it? Dyne, is that American engineering units?
I have no idea.
I like to work everything in SI. My philosophy with anything new is if you don't understand the units of the problem, you don't understand the problem. So that's why I always like to convert things to SI units, just so that I can always confirm that things cancel out. And I have a Word document that I refer to on a regular basis that I created when I was in grad school that basically breaks down like Pascal, Pascal seconds, joules, newtons into their base SI units of kilograms, meters, and seconds. It comes in handy all the time. So I do have this sheet and I do refer to it. So all of like the tips and tricks and philosophies that I say, I actually do this because I'm really not good at calculations, so I have to be as organized as humanly possible. So these are like real tips and tricks that I do to myself to convince myself. When I go into lecture, I'm like, do I actually get this equation? Let me double check the units. Okay, works out. So, energy balance. We're going to redo a new energy balance, but we're going to include this surface energy term. So it should look very similar, except we've added one extra term on. This is a closed system transient energy balance. du is the total change in energy, dt as a function of time. So the only two ways that we can physically interact with this system from an energy perspective is giving it heat, which is Q, and physically expanding it or contracting it, which is the PdV term here. So this term is negative, right? Because as you expand the system, you have to suck energy out of the system and give it to the surroundings. Because you're physically doing mechanical work on the surroundings, and vice versa. This term is also negative because as you physically expand your system, you have to have a greater surface area, which means you have a greater surface energy. We're all good? Okay. So what we're going to do is I'm going to simplify this expression. We want to be able to combine dV and dA. And to do that, we're going to relate it to the radius of a sphere. So we can write that V is 4/3 pi r cubed, or dV, dr is equal to 4 pi r squared, and dV is equal to 4 pi r squared dr. Just a little calculus. Likewise, A, 4 pi r squared, and we'll just jump to the conclusion, dA is equal to 8 pi r dr. So what we can do with this is we can substitute dV and dA into our energy balance, and then we can combine those two terms. We are skosh shy on time, so I'm going to jump over the fun details of it. But effectively, we come up with an equation that looks like this. Looks just like our normal closed system energy balance, except we have a different term for the pressure. It's not just pressure, it's pressure plus this 2 sigma over R. So we're going to call this the internal pressure. So this term is always positive, which means that the internal pressure is always greater than the external pressure. This is the pressure of the system. So if I have an extremely small droplet, what ends up happening physically is that the pressure inside, which basically the net force that the molecules inside are pushing across on the interface, is much higher than you would necessarily anticipate based on the external pressure. That's because it physically cannot expand the system trivially because it'll create more interface. That's why the pressure inside a confined system can be much higher. That has implications in the phase behavior and has all these other different properties that we'll talk about right now. So this is the fundamental origin, basically, for superheating and subcooling. To give you a couple of examples, for water, at standard temperature pressure, when the internal pressure is equal to twice the external pressure, so in this case P internal is equal to 2 times the external pressure surrounding it, this is at a size of about 10 to 20 nanometers. So you have to have a fairly small water droplet in order for the system to be having a double the normal pressure. And this is going to change, of course, based on the surface tension of the surface energy. This is for a vapor-liquid system. So this is liquid water with vapor water. But if you had two systems where, oil and water, something like that, this would obviously change the mathematics quite a bit. This is based on that particular system. So I know everyone is disappointed that we can't go through the math, but basically we're going to talk about fugacity now. So effectively, the procedure that we would take is that we derive that the fugacity of a liquid is equal to the saturated vapor or saturated liquid fugacity times by what we call the Poynting correction. So what we're going to do in the math, or what we would do in the math if we had sufficient time, is that we would substitute that the pressure is actually equal to the external pressure plus the contribution from the surface tension, 2 sigma over r. So then we would just basically break this integral into 2 steps, one going to P, which is the original Poynting correction, and then another one going to the internal pressure based on the surface tension. The net result, however, is what we'll skip to, is that the fugacity of a liquid droplet, right, so this is not an infinitely sized liquid system, this is just the droplet, is going to be equal to the fugacity of that particular liquid at the same temperature and pressure. Right, so this liquid here is that one there. So it has its own Poynting correction already based on getting from vapor pressure to the system pressure. And then it works out mathematically that you get an additional Poynting correction that takes you from P to the internal pressure. So if you were to write this out longhand, you would have basically both of these Poynting terms, for example. But this term is always positive. Now this has implications in the phase behavior. So what this means, and if we do a little approximations, we can write out that the fugacity of the droplet compared to the bulk liquid itself at the same exact conditions, the only difference is confinement. If we assume that V of the liquid is equal to a constant, we can basically do the integration for the Poynting corrections, and we get an expression that looks like this. And this is positive always. Which means that the Gibbs free energy of a liquid droplet is always greater than the Gibbs free energy of the bulk liquid. So this has a couple of different consequences. One, droplets evaporate faster. Or condense faster if you have a bubble inside of a liquid. So let's say, for example, you're designing an engine, right, and you want to inject the gasoline into it. Making small droplets is great because you have a ton of surface area for the volume of fluid that you've injected. That surface area is necessary for the mass transfer process to occur to actually physically get those liquid molecules into the vapor phase, right, because they have to diffuse through the gas. But in addition to that, if you can make your droplets small enough, the fugacity is higher, meaning that they want to evaporate even quicker because they don't want that interface. And the quickest way to get rid of that interface is to evaporate and make it disappear. The second consequence is superheating and subcooling. Now this is the opposite. So in this case here, the droplets evaporate faster, right? This is when you have small droplets already formed in a sea of a second phase, or small bubbles in a sea of a second phase. For superheating and subcooling, you have a single phase and you're trying to create your very first droplet or bubble or whatever the case is. But the problem is that it takes energy to create that interface. Not just enthalpy energy, but free Gibbs energy. Because the fugacity contained inside that droplet is higher than the fugacity of the bulk, that means it's not a spontaneous process. So you can heat water above 100 degrees Celsius and it won't boil because it physically doesn't have the energy to do so. Now there is a temperature at which case that the energy in the fluid is so high that it can form that interface spontaneously, which is what you don't want to do in the microwave. Right? Because what happens basically, if you have a perfectly smooth cup, you put it in the microwave and you superheat that water. When you grab it and you jostle it, that jostles air bubbles into the water. Those air bubbles form an interface. Then the water boils and nucleates on that interface and the whole thing basically explodes in your face. Or it's the same exact thing when you put a Corona beer in the freezer and then tap it. That little tap basically disrupts the interface very slightly and it causes the whole thing to crystallize and precipitate out. But forming that second phase, whether it's ice in water, whether it's water bubbles in liquid water, that causes the formation of an interface. Interfaces have surface energy. So that takes energy to create that interface. So in chemistry class, you might have used boiling chips. Now the reason why boiling chips are so important in chemistry is because ideally, when you're doing chemistry correctly, you should have exceptionally clean glassware. That exceptionally clean glassware you've washed with Piranha or Aqua Regia, or just really scrubbed it with Alkanox, for example. So if you've done that well, you won't have any nucleation sites in your glassware, which means that when you heat it up, you run the danger of superheating it and creating a dangerous situation where it boils over. So because your glassware should be very clean in your chemistry class, you want to put boiling chips in. So what those boiling chips serve to do is they act as nucleation sites because a nucleation site is already an interface that is formed. So it's so much easier for water to go onto that existing interface, create its bubble, and then boil away. So a little fun fact, if you ever guys want to go back to general chemistry, you'll go, I know why we need boiling chips now. I suspect that most of my chemistry did not need boiling chips because I imagine my glassware was plenty dirty enough. So when you're boiling water on a stove top, a lot of times why it boils so readily is that the imperfections in either the metal or you have dissolved gases in the water. So what happens is that water that's being jostled as you're pouring it from the tap has a lot of dissolved gases. Those dissolved gases will boil away or sort of evaporate before the water will, and they'll form little bubbles on your pan, and pots and pans. So that dissolved nitrogen, dissolved oxygen. And then the water vapor will nucleate onto those and then start to boil away. But the whole point here is that interfaces cost energy to form, and that causes superheating and subcooling. Okay. I'm a bit over time, but any questions?
Yeah, one question.
Yes.
So surface tension is going to be constant regardless of pressure and temperature, right?
Everything's a function of everything.
So
no. So technically no, I don't know how strongly of a function it is. I believe surface tension tends to decrease as temperature goes up. I think that's a general rule. I don't know if that can be proven fundamentally, but no, everything's a function of everything. As a default, yes, it changes.
okay.
Okay, and I'll end it.